Weighted number system is a number system where each digit will have a weight or a place value. These are the number systems where each digit or a bit does not have any fixed values. As the name itself says, over here what we have to do is we have to just add 3 to the provided data. Gray code is a type of non-weighted code where each adjacent code word differs only by 1 bit. Hello everyone, I welcome you all to the third session of first sem BCA, and the subject is Digital Computer Organization. Yes, under that we'll be discussing second unit, that's number system. I just request you, before watching this video, there are 2 more videos which is very useful, and all the concepts are being explained in a very smart way. Alright, I just request you to have a look of those videos too. Over here, my name is Deepa Kutnikar. I am working as an assistant professor under Department of Computer Science, Vidhyaashram, Temple of Excellence, MYSURU. Let's start today's session. Before that, let's have a small recap of last session. Yes, in our last session, we had discussed like what is binary addition, what is binary subtraction, and what are the different ways of doing a binary subtraction. Then followed by, we also did understood binary multiplication, binary division, and what is one's complement method, what is two's complement method, how to achieve that. Yes, absolutely. All these things are being discussed in our previous session, that's session 2. Now let's see the agenda of today's session. In today's session, we'll be discussing something called as weighted number system as well as non-weighted number system. We'll be understanding what is this, and also we'll be discussing the examples of this. Followed by, we will also be learning exactly like what is a BCD that we have already learned and we were using, but we'll be understanding exactly what it is in this session. Up next, we also will be discussing the gray code, binary code, and XS3 code, gray code, etc. So this is all about today's session. Now let's start with understanding what is weighted number system. Weighted number system is a number system where each digit will have a weight or a place value. Alright, up next, we can also say the value of number is determined by multiplying each digit by its weight and adding up the results altogether. Also, we can say weighted number systems are used in various applications with arithmetic operations, coding, as well as in digital electronics. So this is nothing but weighted number system, and let me tell you, this is one of important topics with respect to exams or internals point of view. Alright, so let's move forward, and over here let's understand the weighted number system with a simple example. So under weighted number system, we'll be considering decimal number system. Yes, this is one of an example of weighted number system. As we know, this is represented by using base 10 that we have already discussed in our session 1. Now let's see how to represent these values. So we have an example, that's 456. Now let's see how this 456 is represented by using decimal values. So over here we have to start from units place, that's from 6. So 6 into 10 power 0 will give us a 6 because 10 power 0 is 1. So 6 into 1 is nothing but a 6, followed by my next bit, that's a tens place. So how to represent tens place? That's by using 1, 10 power 1. So it's 5 into 10 power 1. The answer will be 50. Alright. Up next is my hundreds place. So for hundreds place, what we have to represent it as? It's 4 into 10 power 2. So the answer will be 400. And finally, what we have to do? We have to add all these things. That's 400 plus 50 plus 2. So the final value is 456. So this is a primary example of weighted number system. Up next, let's see one more example with respect to our weighted number system. It's none other than binary number system, which is having a base 2. Alright, so in the system, as we know, we are working with only 2 values, that's either 0 or 1. Now let's consider an example. That's 1101. How to represent this? Yes, absolutely. That's by using positional value. Only because of that, this is called or this is considered under the weighted number system. Let's see how this is performed. So again, let's start with the LSB bit. That's 1. 1 into 2 power 0. Why 2? Because we are working with binary number system and the base of the binary number system is 2. So I have to write 2 power 0, which gives me an answer of 1. Up next, it's 0 into 2 power 1. The value is 0 into anything. It will be a 0 itself. And up next is a third bit. That's 1. So for the third bit, what's the position number? It's 2, right? So 2 power 2 is nothing but 4. 1 into 4 is nothing but 4. Yes, done. Again, I have a fourth place. So the position number is 3. So how it goes? 1 into 2 power 3. 2 power 3 is nothing but 8. So 1 into 8 will give us an answer of 8. And finally, what we have to do? We have to add these things. So 8 plus 4 is 12. 12 plus 1, 13. Yes. So this is how we'll be considering this binary number system as a part of weighted number systems. Up next, let's see what is non-weighted number system. Over here, we can consider these are the number systems where each digit or a bit does not have any fixed values. So that's why it is called as a non-weighted number systems. So now let's see what are the examples. So the examples for this is gray code, XS3 code, etc. Alright. Followed by, let's see the application, like where these non-weighted systems are used. It is used for error detection and correction. If any errors are there, then we can correct them by using this non-weighted codes. And the next one is digital to analog converters, which we call it as a DAC. Yes, absolutely. In this conversion techniques, this gray code is used. So why is it used? In order to reduce the errors and improve the efficiency. Up next, let's see the next application. So non-weighted code is also used in finite state machines. So let me tell you, this finite state machine is one of a very important algorithm that we do use in our gaming, or we can say it is used in creation of games. All right. Over here, we will be using one hot code. Yes, this is also a type of non-weighted code, as we have XS3 and gray. In the same way, we have one more type of code, that's one hot code. Okay. And that is being utilized in a finite state machine. Next application is it is used in digital controllers. It is used in digital controllers, which is it? One hot code itself is used in digital converters in order to improve reliability. Up next is a communication systems. In almost all the communication systems, we will be using the non-weighted codes in order to detect as well as correct errors in data transmission. So these are few prominent applications of non-weighted codes. Now let's see something which is called as binary coded decimal, which is nothing but BCD. So you might remember, if you have watched the previous sessions, that's session 1, in that for interconversions we had utilized one format, that's 2 power 0, 2 power 1, 2 power 2 and 2 power 3. That representation is nothing but a BCD. So now let's understand it in a very good way. Yeah, a binary representation of decimal numbers with each digit represented by 4 bits is called as BCD. Alright, now we can see it has a binary representation of decimal numbers where each digit is represented by 4 bits and each decimal digit is converted into the binary equivalent. So we can see an example over here. We have 18, that's in decimal value, and we are converting it into BCD. That's by using this one, 2 power 0, 2 power 1, 2 power 2 and 2 power 3. Alright, so this is the representation what we use, and by using this we can see we have converted our values to binary format. Now, let's see in depth like how this has been done. By using this table, you will be very clear. So, you can just observe we have directly written 8421, which we have got by using this representation itself. That's 2 power 0, 2 power 1, 2 power 2 and a 2 power 3. Now 2 power 0 is nothing but 1, okay. 2 power 1 is nothing but 2. 2 power 2, 2 square is a 4, followed by 2 cube is none other than a 8. So, in general, we call this BCD as 8421 code. That's 8421 code. And if I want to represent my value 9, how to write it in a binary form is, I have to just add the place values. Let's start doing it. 9, I want 9, right? So, by using which columns I can get a 9. 8 is nearby to 9. So, I need this 8. And what is remaining? Out of 9, I have already represented 8. And the remaining but is only 1. So, I have to write a 1 under 2 power 1. And what about the rest 2 bits? I have to just add a 0 because I have to adhere with this 4-bit representation format. So, in the same way, we have completed all these things. That's from starting 0 to 9. You can just see and verify how the things will go. Alright, so this is all about the BCD representation. Up next, let's go with addition of BCD numbers. Now, let's go with addition with BCD numbers. So, yes, over here we can just go with BCD numbers addition. That's bitwise. And the thing is, if our result will be greater than 9, then there is some rule or there is a condition that whenever my value is within 9, I can execute it as it is. But in sometimes, we can't say the answer will always be less than 9. It will be greater than 9, right? So, at that time, what we have to do is, we have to add the final answer with a binary 6. Please remember, with a value 6. That's a binary 6 in order to correct my output or in order to correct my final result. So, that's a addition with BCD. Now, let's see an example over here. We have considered 18 plus 27 and we have represented in a binary format. You can just observe over here, the final bit value is greater than 9, which says 1111. In the sense, it is 8 plus 4, 12, 12 plus 2, 14, 14 plus 1, 15. Oh my god, it's truly greater than 9. Now, for that, what we have to do? I'll be adding 6 with this. So, the value what I get finally is this one. So, this is how we'll be performing addition with BCD. Now, let's see an example with respect to BCD addition. So, yes, we have considered this. That's a 4 and a 6. And let's start doing it. 4, it's 0, 0, 1, 0. Alright. So, what is this? It's a 4. Up next, I have to get a 6. So, how is it? I have to write in binary form. That's 0, 1, 1, 0. Finally, what we have to do? We have to add this. 0 plus 0, okay, 0, 0 plus 1, 1. 1 plus 1 is a 0 and a carry 1. 1 plus 0, 1. 1 plus 0, 1. So, the value is 1, 0, 1, 0. Now, let's check, is this value greater than 9? It's 8 plus 2, 10. Yes, absolutely, it's greater than 9. So, what we have to do? We have to change or we have to add a 6 to this number, okay? So, this is the second step. What's that? I have to consider this. That's 1, 0, 1, 0 and I have to add a value 6. It means 4 plus 2 followed by 2 zeros. Now, let's simplify this and let's check what we get over here. 0 plus 0, it's a 0, alright. 1 plus 1, sum is 0, carry is 1, 1 plus 0, 1, 1 plus 1, it's again a 0, followed by carry 1, again 1 plus 1, I'll be getting a 0 with a carry 1. Now 0 plus 0, I'll be getting a 0 and followed by 1. So this is my final answer. And now how to represent this? As we are dealing with 4-bit format, let's write this completely in 4 bits. Okay. So now we have single bit over here, right? 1, 2, 3, 4 followed by one single bit. Let's write it in a 4-bit format itself. So it will be 0, 0, 0, 1 followed by 4 zeros. All done. Now let's check, am I getting a right value? So what is the decimal equivalent of this 0, 0, 0, 1? It's a 1. Followed by 0, 0, 0, it's a 0. So this is a decimal equivalent and this is a binary equivalent. And let's check, what is 4 plus 6? 10. Hey, yes, we got a value 10. So my answer is right. So did you understand why we have to add a value 6? By adding a 6, I can get an correct result. So this is how we will be doing or we will be performing the BCD addition. Now let's see what is XS3 code. So this is an example of non-weighted code, right? Now let's see how to perform this. XS3 code is where a decimal digit is represented by its binary equivalent plus 3. As the name itself says, over here what we have to do is we have to just add 3 to the provided data. Alright, so let's see with an example, it will be helpful for you to understand. Over here we can check, we have a 0. So for this 0, if we add 3, what's my answer? It's none other than 3. So that's my XS3 value. So next question is 1. So if I add 3 to 1, what should be my answer? It's 4. So yes, over here you can check, I have got a binary 4. So that's what, nothing but XS3. XS3 in the sense we are adding 3 for all the data. Up next it's a 3 and for that I have to add 3 more. 3 plus 3 is a 6. I have to represent it in a binary format. So let's see how to represent 6. It's 0, 4 plus 1. It's a 6. Next 4. 3 plus 4 is 7, right? Okay, then my answer will be 0, 1, 1, 1. Followed by 5. 5 plus 3 is nothing but 8. So I have to just write it in a binary format. So this is how the XS3 code can be achieved. This is all about XS3 code, which is an efficient example of non-weighted number system. Up next, let's see what is gray code. Gray code is a type of non-weighted code where each adjacent code word differs only by 1 bit. Alright, now let's see where is it used. It is used in digital to analog converters as well as also utilized in the communication systems. So this is a gray code and let's see how to perform the gray code conversions. Over here, this is very simple and easy. You might have learned with respect to XOR gates. If not, okay, let me write over here. We'll be having 2 outputs, that's A, B and Y equals A XOR of B. Now, I'll be having 4 different outputs, 0, 0, 1, 1, 0, 1, 0, 1. For this, we'll be getting a high value only when my inputs are differed. If my inputs are same, I'll get a value 0. So this is a XOR gate. So this is a truth table for XOR gate and we do follow it in order to represent our gray code. Now let's see, we have a provided data that's 100110. How this is calculated is we have to retain the first MSB bit. Okay. So alright, I have retained the first MSB bit. Up next, what we have to do is we have to go on XORing the adjacent values. So 1 XOR 0, it's 1, correct? Again 0 XOR 0, 0, 0 XOR 1, 1, 1 XOR 1, it's none other than 0. Why? Because I have same input. Up next, 1 XOR 0, I'll be getting 1. So this is the binary code. It's been converted into gray code. So this is how we can convert from binary code to the gray code. Clear? Up next, let's solve an example over here. Let's write it 1 0 1 1 0. All right. Now what I have to do with MSB bit, I have to retain it as it is. So let's retain it 1. Up next, I have to go on XORing. 1 XOR 0, inputs are different, so I'll be getting 1. Next, 0 XOR 1, and input are different, so I'll be getting 1. Up next, 1 XOR 1, same input. So what's the answer? It's 0. Up next, 1 XOR 0, input are different, so I'll be getting a value 1. So finally, what's my answer? It's none other than 1 1 1 0 1. Easy, right? This is how we can convert our binary value into the gray code by using XOR gate. Let's see how the values from gray code is again been converted to binary. So for this, we will be also using the same gate, that's a XOR gate, but the representation is different. So now let's see how it goes. So in the previous thing, what we were doing, we were just XORing with adjacent values, right? Over here, we have to retain our MSB bit, alright. Up next, what we have to do? We have to consider the answer, previous answer, XORed with the adjacent value. So 1 XOR 1, both are same, 0, 0 XOR 0, 0, 0 XOR 1, both are different, so we'll be getting 1, 1 XOR 0, both are different, so 1, 1 XOR 1, both are same, so we'll be getting a value 0. So this is how we'll be getting, or we'll be converting from gray code back to binary code. So this was with respect to today's session. Thank you. And yes, I wish you all the very best for your internals. Please do watch all the 3 sessions with respect to your unit 2. Thank you.